Hello everyone, welcome back to Computer Science 354 at the University of Wisconsin-Madison. This is Machine Organization and Programming. We're beginning week 3, talking about pointers and arrays. Alright, but let's get started with just a quick review, sort of to nail down our place in the course so far. We began the course talking about programming in C. And so far we've covered the basics of control flow and data structures. So in control flow, we have conditionals like the if statement. Loops, we talked about the while loop, the do while loop, and the for loop, and just basic function calls. Also in this control flow section, we've got the switch statement. I'm not going to go into that. We're not going to deal with the switch very much other than it might be in some menus that I write for the homework assignments, but I'm not going to ask you guys to write one. It's there. Look up how to do it. Works the same as most other languages. But we're not going to be diving into that when we make the connection to assembly language. So I'm going to just skip over that. And then as far as data structures go, we covered the primitives. So we started looking at char, int, float, and double, the 4 basic data types. Then last week we talked about how to create our very first one-dimensional arrays. Today we're going to be looking a little bit more at character arrays and the one little difference between character arrays and arrays of integers. And we introduced the idea of pointers. Today is going to be a deep dive into pointers and arrays. All right, some things coming up. I'm also going to skip over enums. They really go hand in hand with switches. There'll be some examples where I use these in the homework assignments. You'll see how they work. Look up how to use them if you're interested. We probably won't do more than that in this class. And then today we're going to spend about a third of the class talking about multidimensional arrays. In particular, the memory model, how C is going to, when the compiler runs, allocate memory on the stack or on the heap for these multidimensional arrays and primitive arrays too. We'll start with those. And then we'll wrap up with an introduction to structures. If you're familiar with classes from other object-oriented programming languages, structures are the C version of that. So C is not an object-oriented programming language. We don't have classes, but it's a composite data structure that lets us do things a lot like classes where you have containers for data, but it doesn't let us have functions that go along with them to process those pieces of data. So technically we're not creating objects, we're not having functions that operate on them, but we will have data packages. All right, I'm going to jump back over to a CSL machine. We'll pull up some code, and the way I want to approach this today is to just start off with a quick review, and we'll do some, experiments. I kind of want to show you guys, if you're trying to learn a brand new programming language on your own, how I approach this by just learning a little bit, try an experiment, and see what happens. And at the same time, we're going to try and learn about how the compiler is allocating memory to go along with all of these data structures. So that's the goal for today. Once again, let me hop over to a CSL machine and pull that up. All right, I'm back. I'm actually using PowerShell. This is my local machine. I was getting some truly horrible lag trying to deal with the CSL machine just now. And so I'm just going to scrap that and go with PowerShell. I don't have Vim installed on my computer, so I'll be using Notepad++. It's the lowest level editor that sort of gives me the features that I want. And I don't want to use a powerful IDE package today that might hide some of the details that as I want to remind myself what I need to talk about. So that's what I'm going to be doing for today. So as you can see here, I've got my teaching directory where I've created a demo.c file to get us started. When I compile this, this is going to go by really fast from now on. I'm using GCC as my compiler on this computer. If you guys don't have a C compiler installed on your Windows machine, I installed the min-gw package to give me the Windows version of GCC. I'll go ahead and write a note to remind myself to put that in the description. It's kind of a pain to install. Just find some directions and go through those. Follow along with the directions and it'll get you there. All right, I named it demo.c. I'm going to be using the M32 to compile my code for 32-bit machines for everything I do today. This is going to give me 32-bit addresses when I look at all the addresses that are stored in pointers. It means that my pointers will be 4 bytes because that's 32 bits, as opposed to the default 64 bits that my machine's going to give me. And I'm going to have all the warnings turned on because I make tons of mistakes and I want to be able to talk about them and talk about good coding practice. All right, so let me just go ahead. We'll run the compiler right here. My demo program, when I compile on a Windows machine, this is going to give me a .exe file for an executable file. And to run that, I need to use /demo.exe. And if you screw this up, if you're doing PowerShell, if you're trying to follow along on your own computer, it'll give you a message. So all this program does right now so far is print out welcome to week 3 of CS 354. Let me pull that up. I just wanted a framework to get started when I just needed to know that it compiled and I didn't have any dumb mistakes in there. All right, so I'm going to go ahead and I'm going to write a little bit of code. You guys can pause and copy the code in yourself as soon as I get this written. I'm hoping that if I just pause the recording, it'll speed it up a little bit for you guys. The video will be a little bit shorter. If you're reviewing this later, before the exam or something, you can watch it on double speed and not have to watch me type anything to get a good review. But at the same time, as you guys are going through watching this for the first time, you should have the video pulled up. And today is one of those days where you should follow along and do everything yourself. You're going to make little mistakes. You'll have typos in there. They're going to give you error messages. All of those are very informative. You'll learn a lot more by making a typo or getting a result that's different from what I get. I'm on a Windows machine. I'll explain what I see and why my compiler is doing what it's doing, why the memory is allocated a certain way. Your machine's probably going to be different. It's not going to use the same memory addresses. It might do things in a different order. And those are all very informative learning opportunities. And if you get something really, truly weird, throw it on Piazza and we'll go through it and break it down. And it's going to be a great opportunity for everybody in the class when those things come up. All right, so I'm going to pause now and write some code. All right, so I just finished writing a little bit of code. This first piece here, starting on line 7, we're just going to do a quick review of pointers and what they do, and then I want to take this and try and connect it very deeply to the memory model, what's going on inside the machine. So I've just created two integers, a and b. I've given them some values, 3 and 4. Then I've created 2 pointers. Remember that anytime I have the name of a type, like int here followed by a star, this is going to be the creation of a pointer. In a little bit, I'm going to be using just the star without the type there, and that's going to be dereferencing the pointer or following the pointer to the data. Okay, and this first pointer, PA, is a pointer to variable A, and I'm giving it the address of A so that it actually stores, pointers store memory addresses of other variables. Same thing for B. So I'm creating a pointer to variable B, so P for pointer, B for B, and giving it the address of B. Then I'm just going to be printing out everything I can possibly think of about these things. So for A and B, they're just integers. They contain a value. So %d is going to print the decimal version of that value right there in A. And I can print the address, and that's going to be %p to get the pointer code or something that's going to print in hexadecimal, I guess. And I'm going to give it the address of A. Remember, the ampersand is the address of operator. I'm going to do the exact same thing for B. I just wanted more than one thing, so when I draw the picture of the memory model, I've got like some actual stuff there and it's not looking pretty empty. I'm going to do the same thing for my pointers, PA and PB. I'm going to print out everything I know about them. So first I'm going to be dereferencing them, and because they're integer pointers, this will print a decimal value. The %d is the format code there. I'm also going to be printing the actual value, the contents of that pointer. And again, pointers store addresses, so I'm using %p to get a hexadecimal memory address. And then I'm going to print the address of PA, where this is actually stored. So here's the dereference, here's the actual contents, and then this is the address of PA, or where PA is stored in memory. And then the exact same thing for PB. All right, let me pop back over to PowerShell. I just got this to work, I tested it, I didn't make any mistakes. So here's what we're looking at. A contains 3, B contains 4. That's exactly what I initialized them to. That's looking pretty good. We can see that it's storing A at hexadecimal value 0061FF1C. From now on, I'm going to abbreviate these. I'm just going to be talking about the FF1C, or maybe even just 1C, because they're all going to be really close together, and I don't need the leading digits there. I mean, all of these, 0061FF, 0061FF. I'm going to stop repeating that. And until we're getting to, all of these memory addresses are on the stack. They're all very close together. When we have memory addresses for things that are not on the stack, then I'm going to highlight the difference, and the leading digits will be different in that case. All right. And again, let's see here. I'll pause this for a second. Just which one of these is bigger? Is 0061FF1C greater than or smaller than FF18? Which one comes first? Just pause the video, make a guess, figure it out. When we draw the picture of the memory in just a second, I want to make sure I put all of these in the exact right order, so you guys can check and make sure that it matches. All right, and then with the pointers, so I've got a pointer here. When I dereference it, that means follow the address stored at that pointer and go get the actual data. So that's 3. It's a pointer to A. It's getting that number right there. The actual pointer contains an address. So 0061FF1C. This address right here is the address of variable A. So this was the address of A. That's the value contained in this piece of data right there in that memory location. And the address of PA is, so PA is a pointer. It stores a memory address. It's actually located in memory itself. And I can go get the memory address where it's stored. I can see here this is at FF14. Again, is this bigger or smaller than FF1C, FF18? I want to make sure I put these in the right order, so you guys need to check me. All right, and then same kind of thing for PB. It contains the value 4. The address it points to, 18, is the address of B. Perfect. And again, it's got its own memory location. In this case, FF10. All right, so I'm going to just pause the video. I'm going to go pull up a PowerPoint slide, and I'm going to, actually, I'm going to grab a screenshot of this one right now. Pull this up in PowerPoint and draw a picture of what's going on in the memory. 1 second. All right, guys, I just started making this picture using the PowerShell data, and I was trying to put these addresses in. I'll show you that slide in a minute. But this just struck me as really weird that these were so small. I mean, they're starting with 00. Now let me take a look at this. I haven't introduced this idea yet, but all of the space, all of the memory that your program gets is divided up into a bunch of sections. Up at the very top, like address 0 is reserved. We can't use address 0. And I'll talk a little bit about that. We're frequently going to set uninitialized pointers to address 0 because it cannot be used. We cannot write there. And that way we will know that that pointer is uninitialized. It'll cause the code to crash. And crashing is better than weird random errors that are unpredictable. So that's like safety. We'll talk about that in the null pointer section coming up soon. Then after this reserved memory, is memory reserved for the actual instructions. When I compile my code, it generates those binary numbers that represent the instructions. The CPU fetches, decodes, and executes them. Those are stored up at the top at very low memory addresses. Below that, below the code section, and I should also mention that sometimes the operating system, for security reasons, will offset this code by a random amount, so it makes the addresses unpredictable. So address space randomization means that it's a lot harder for someone to hack your computer if they don't know where the instructions are. And they'll just put a bunch of like reserved blank space in between the code and address 0. All right, so this is unpredictable where this is in general. Following the code, oh, by the way, if you get the chance, computer security is an amazing class. I highly recommend it. 640 or something like that. I might have the number wrong. Great class. Anyway, after the code section, the compiler is going to reserve space for any of the text that's hard-coded into the program. Like right here, I've got this welcome to week 3 of CS354. That code, the representation of that text is going to be in this section right here for text and for global variables. Anything that I need, that I know I'm reserving space for global variable, will be in this section up here because it's going to be accessible to any of the functions. Below the text section, we have the heap. The heap is for dynamically allocated memory. That's next week's topic. Right now, we are not using the heap. It should remain at size 0. We're not using any of it. But as we dynamically allocate more and more memory, it's going to grow from address 0 up the top here to larger and larger numbers. The rest of the memory is the stack. Now, the stack is where all of the functions are going to reserve memory for their local variables, for parameters. I've got the list right here. For parameters, for local variables, and returning information. And the kinds of things it needs, if it's a function that has a return value, it'll reserve space for that return value. Like main, for example, returns an integer. It also needs to know the return address, so where to jump to. In this case, PowerShell is going to be the bottommost frame. PowerShell is what I'm using to call my demo.c or demo.exe function, and that has a main function. So when main is done running, it's going to return 0. and go back to PowerShell. So there's a return address into PowerShell's code, so it knows where to go. Anyway, we don't have any parameters. There was no command line arguments, so that's all going to be just 0. For his local variables, I don't have an array yet. That's coming soon, but I do have A, B, PA, and PB. So those are the local variables. They're going to be stored on the stack. Now this typically starts out at really enormous addresses, the end of the address space, and grows towards smaller numbers. If I write a function in main and call that function, or if I call a function from main, it's going to get a new stack frame or a new activation record with all these things. It's going to have space for parameters. They're going to reserve space for local variables, return information, the return address, the return value, some pointer information to remember where all of how big the stack frame in main is. That'd be the base pointer. We'll come to that in the middle third of the class as we break down what happens with a function call. But so this struck me as really weird that it starts with 0, 0, because the stack starts at the very, very largest addresses. And apparently PowerShell is just not giving my program very much space to run. It doesn't need very much space. It's got 4 variables and just prints them out. It doesn't need it. We're not using a huge amount of memory. But it seems weird to me. And so I wanted to go and compare it to what happens when I do log into a CSL machine. The lag was still bad. I'm going to stick with PowerShell for the rest of this lecture. But there's some differences. So on the Windows machine on PowerShell, the blue one, I'm using MinGW as my compiler, which mimics the GCC that we see on the Linux machines. The Linux machines, of course, is using GCC, the GNU-C compiler. Here I'm using the same command, mem32, all the warnings, same file name, same file, just copied it over to the CSL machine. It's printing the same stuff. But now check this out. So A is still at value 3. That's good. Address of A is now, and again, here's the difference. It's printing the 0x when we use the GCC compiler. So Printf on the Linux machines is slightly different than the Printf on the MinGW compiler, because this did not print the 0x for the hexadecimal. And it's also using the much larger address space. This is an image I can't highlight, but it's starting at FF, the very largest, bottommost addresses that are available. And FF, and all these start out 0061, nowhere near the end of the address space. Okay, second difference, when you count by 4s, because all of these, a pointer is 4 bytes, an integer is 4 bytes on a 32-bit machine. So we'll start with 10, 4 bytes later is 14, 4 bytes after that is 18, 4 bytes after that is 1C. It starts out here with the, PB, the pointer that I defined last, is at the lowest address. And so 10, 14, 18, 1C. It's just counting up in that order. Now check this out. Maybe a little easier to see. We've got 90, 94, 98. They're in the reverse order. So the takeaway message from this experiment is that the compiler has a lot of control over where it's deciding to choose to put things. The writers of compilers at some point needed to make a decision. So I have a function. It's in this case main. It's reserving some space for some local variables. Where am I going to put those? What order am I going to put them in? And so they had to make a decision about what order they went in, and clearly the writers of this compiler chose a different order than the writers of this compiler. They're backwards. All right, for the rest of this lecture, I'm going to continue using PowerShell and Notepad++, the Windows machine version. Be aware that there are some differences. If anything strikes me as weird that I suspect will be different, I will go back over to the CSL, deal with the lag. I know I can edit all of that out, and you guys will never even know that it's pretty bad today. And now that I think about it, I wonder if the lag is coming from my son's room where he's playing video games. It might not even be the CSL. It could really be my local problem. But I'm going to keep going with the local machine, and anywhere there's a difference, I'm going to pause and point that out. All right, 1 sec. All right, guys, I just put these things into a PowerPoint picture of the memory. So what we're looking at right here, this is the screenshot from the output from my very short pointer review program. Over here, I've got a picture of what's going on in memory. Now, memory in the computer is just a linear array from address 0 up through some maximum value of addresses, and each of those addresses will be holding 1 byte, so 8 bits of data. I've got these blocked into groups of 4 because all of the data that I'm looking at right now are either integers or pointers, and those are all 4 bytes. In memory, each of these, each byte is going to be represented by 2 hexadecimal bits, so there's 0061 FF818, means that we've got all 32 bits accounted for in hexadecimal, or 8 hex digits. And again, as I've got the picture here, I've abbreviated all of my addresses. This 00 right here, I intend this to be 0061FF and then 00. And so like right here, I've got 1C. If I go down to this 1C right here where I've got variable A is going to be this 0061FF. I left off the 0061FF just to shorten this all up. So at 1C, I've got the data for variable A. And what's in this location is just the number 3. And again, in binary, that's going to be 32 bits. The first 30 of them are going to be zeros, and then we've got 1, 1. And again, for B, this is going to be a binary. It's going to have 29 zeros, followed by a 1, and then followed by 2 zeros after that. When the computer uses this memory, it doesn't know how many digits we have. It doesn't know how many significant figures there are. It always uses all 32 bits. That was one of the questions that came up on Piazza, and I just want to make sure that everybody gets that message that even though it's a number that's only like 3, very small, it still uses the exact same amount of memory as 30 million does. And every calculation the computer does, all of the bits go through. So if I add 3 plus 4 together, all 32 bits go into the adder for both 3 and 4. It adds the first 30 zeros together. It adds the first 29 zeros together for A and B. They're all there. They're just used in parallel, so it's very fast. Okay, so anyway, that's my picture here. I've got the memory addresses here on the left. I've got the data that they're contained. And then I jotted down, and in fact, maybe I should put these in parentheses just to kind of remind us that after the compiler runs, these names are no longer needed. They're completely obsolete. The compiler doesn't keep this. The only thing the machine cares about is the memory address. That's what it's using for all of the names. It doesn't care about A, B, PA, PB. It only uses memory addresses, 0061FF18. And they get replaced. Essentially what the compiler does, first time it goes through, it sees int A. It's going to say, okay, I need to remember A. So it puts it in what's known as the symbol table. And then it says, okay, it's an integer. Go grab 4 bytes from memory somewhere. And says, all right, let's, here we go. Here's 1C. And it just remembers that A is in the code. The computer needs to know 1C. And it gets replaced. By the time this is compiled, and you're looking at the binary code that's executable, there is no A anymore. That's gone. It's all been replaced with 0061FF1C. Anywhere there's an A, it's now that binary code for that address. Anyway, but I jotted these down to make it easier to understand that this is where things are going. All right, next up, so A contains 3, B is 4. I've got these addresses. On the Windows machine, this is in the reverse order that I declared them. On the Linux machine, they were backwards from this at different addresses, but I'm sticking with this version. All right, and then when I've got my pointers at FF14, I've got the pointer A, PA. This contains a memory address. So this address, 0061FF1C, check it out. Let me see if I can highlight and get it to show up. It doesn't work. Okay, so this 1C is actually this 1C over here. I really hope my mouse pointer is recording because this is going to be a lot of garbage if it's not. You can't see where I'm indicating. Yeah, that 1C and that 1C are the same. So let me see. Let me grab an arrow. One sec. I think I can do this pretty fast. Where's the arrow? We need the good arrow. There it is. Top that down. So right there. PA. Shrink it. Points to right there. So anytime I use the star, so PA, the compiler sees a PA, it goes, it grabs this address right here. It's got this data, this address, 0061FF1C. The star says, okay, now go to that address. So it goes, I've got 1C, it goes to 1C right here, and then gets that 3. That's what the star means. It says, go get the address, and then follow that address and get to that number. All right, I've got another pointer here. I'm just going to real quick make this a little more confusing, we'll add a second arrow because PB is pointing to that spot right there. I know I've got two arrows on top of each other. Hopefully that's not too confusing the way I built it up. Maybe you guys let me know if it is in the comments, and I'll stop doing that. If it works, don't do anything. All right, so next up, I feel like this is a great introduction to pointers. The next thing I'm going to do is go put together an array in memory. We'll print that out, and we'll look at all the same information, and we'll start talking about how the computer is going to deal with arrays. 1 second, let me go build that, and I'll be right back. All right, guys, I'm back with my next example. I've gone and created a simple array, just an array of integers. It has 5 numbers in it, 0, 10, 20, 30, and 40. And then I'm just going through. So I've got a for loop, and I'm just printing them out. So I'm printing out array. This is going to be array 0, 1, 2, 3, 4. And then the decimal value of that array entry, so 0, 10, 20, right like that. Then at address, and then again my little prompt saying array index 0, 1, 2, 3, 4, and the address that it's actually at. So to get the address of an array element, I need to basically use the index notation to go get that array element and then give it the address of operator. All there is to it. When okay, so pause the video, go ahead, put this code into your own machine. It took me 4 lines to add a couple things, and run this yourself so you can compare the memory results that I'm getting with what you're seeing, and just make sure that you understand there's likely going to be differences between my picture and yours. All right, let me pop over. I already ran this on PowerShell. Wait, one more thing. So this is sort of a nice, easy way to just do it, but I've hard-coded a couple things right here. First, I've hard-coded the number 5 as the size of my array. And then I've got an array 0, 10, 20, 30, 40. A better way to do this, instead of hard coding the 5 in and having to type it twice right here, would be to use a variable. Let me go ahead and real quick. And the way we do this typically in C is to define a variable. And define variables, these are, when I'm using define, anything that begins with the hash is going to be a compiler variable. So I'm defining a compiler variable, not a C variable, something for the compiler. And I'm going to call it array max, like that. I'm going to do it all caps. And then to define a compiler variable, there's no equals, it's just the name of the variable and what I'm defining it as. So I'm going to copy and paste this in place of my 5 here. There we go. And the other thing I'm going to do, in case I want to go back and change this and make it smaller, rather than hard coding my numbers, I'm also going to use a for loop. Less than array max, I plus I equals I times 10. Okay, there we go. Now this should give me the exact same thing, but now I'm using much better programming practice and not hard coding any of the sizes of my arrays. Part of the reason I wanted to do it this way, using the constant or the compiler defined variable, is that in C, I'm going to speak very, what's the word? Inaccurately, I guess. Supposedly requires that the compiler know the size of the variable ahead of time, the size of an array. It must be compile time determined. It's not entirely true. They've added variable length arrays in actually a revision that was quite a while ago, so C no longer needs to know the size of an array ahead of time, but older versions of C definitely did. So we still see this kind of structure where we define a compiler variable, and this is just find and replaced in the code. So the very first step, we had 4 steps to the compiling process. The very first step dealt with all of these compiler commands. So include just copied and pasted the entire file, standard.io.h, and define is just going to find and replace anywhere that we've used array max and replace it with the number 5. All right, that's all I wanted to say here. Let me go back over and show you the results. Okay, so I compiled it without that change. Let me click recompile. I didn't save it. Save. Compile again. Clear that, and now let's run this. There we go. Now, check this out. So I've got the old code right here. I already see one difference because I've got the other monitor open with these addresses. The address has changed just by a little bit. So I'm going to go grab a screenshot of this and pull it up, and we can compare the old screenshot with the new screenshot of where these things are and talk about why they changed. And then I can see that I've got my new information about the array. So in a screenshot, I'm going to talk about these addresses and how the compiler chose to lay these out in memory relative to this other data that we've got in there. Let me go do those things I just said I was going to do. All right, guys, I made a new slide. I've got the old version up here with the original addresses for that program I just declared 2 integers and 2 pointers. And then here's the new version, the upgrade, where I've created a 5-element array. And I've printed out the values and their addresses. And so check this out. If we just look at this very first variable A is located address FF14 in the new version, and it had been at FF1C. So this is the picture of the old version. At 1C right there, I've got A, and this is moved to 14. So it moved up by 2 addresses. And in fact, we can see they're all in the same order. It's just shifted this entire block up by 8 bytes. So pointer B is now at 08. A is at 14, so shifted by 2 lines. So I'm going to go ahead and I will change this for this example, but from now on I'm probably not going to adjust that when they move things around. So chances are, if we go back 2 slides to this picture where I was looking at things, something changed down here in the stack frame for PowerShell, and it needed more space. I did run some more commands, probably expanded the history. I'm not sure what it is. I'm totally guessing here. Something changed that. We recompiled and we changed the length of the code. So the code is no longer, because I've got extra code for that array. And there's now more global data, more text. And let me pull this up. In this right here, printf address of, it's now got this text also stored in the text section right there. Still not using the heap, nothing dynamically allocated. And then, of course, we now have the array that's also going to be stored with the local variables in main. So main has reserved a little more space for local variables. And I'm not sure, but all of those things caused something to change. But it was a minor change, and we just see these addresses shift by 2, the size of 2 integers, 8 bytes. All right, so let me go ahead and put all of this in the picture. The other thing I noticed, and so this is going to be a problem, is that we're looking at here, the very last entry, FF04, is right here, FF04. And then we've got FF00, and then we're off the top of the picture. So I'm going to shift this whole picture down a little bit so that this FEF4 address is actually not off the screen. So this is why this lecture takes so long to record, because I keep having to redo the memory picture after I do an experiment. All right, give me a sec. Let me go put this picture together. All right, I've got this put together now. So I've gone ahead and shifted all the addresses. I had to add an extra digit because we're now spanning from E, E4, E8, EC, EF0, EF4, EF8. Here it rolls over to the next hex digit in the 3rd position, so E to F. So I needed a 3rd one. And we got 48C, 048C, 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 04. It looks like I didn't make any mistakes yet. If I spot one, I'll get it fixed. All right, and then these addresses moved for all of these first 4 pieces of data from my first experiment. I got A, B, PA, and PB, so I've got them moved. I forgot to update those addresses. Here, oh, hold on, time out. So PB actually holds an address 8 less, that should be at 10, and PA is actually at 14. Okay, now that looks good to me. So the next thing I've done is I've gone ahead and added in the array. So I can see that my array, 5 elements, numbers 0 through 40, increments of 10, are at these addresses, 0061 FE4, or EF4. So at EF4, I've got the 0 right here for array element 0. EF8 contains array element 1, so 48C04, 48C04. So that's what they're looking like in memory. Couple little things. Notice that the compiler chose to allocate all of the memory, and we're using these sort of in reverse order here. So A was the first thing initialized, B was the next thing, PA, then PB. And then the array came next, But the array elements are in the reverse order from that. They're in increasing order. So element 0 is up here and then 1. So they're, I guess the moral of the story is the compiler designers can do pretty much anything they want with their array, but with it, how they allocate memory for variables. But typically what we'll see with arrays is that the very first element is at the lowest address. And as you go across an array or along an array, we're going to see them at increasing addresses. I'll pull this up on a Linux machine and make sure that that is true there also. Actually, let me go ahead and do that right now. Yes, that is true. So check this out. Here we're going F00, F04, F08, F0C. Okay, but then over here we've got F18, F1C, F20, 24, 20, 24, 28. These are all in increasing address order. And there's also, they've shifted around a little bit. So this first one was, let's see here, DF0, DF18. So these are again above this in the memory space. So it's the compilers reserved a block of memory for all this stuff. And then at the very top address, the lowest address, it's putting in A, then B, then PA, then PB, F0C, right there. And then it skipped a bunch of space. There's some empty space there between F0C and F18. So I've got F like 10 and 14 are both empty, not used in this particular example. I'm not going to draw the picture of that, but just an observation. But the point I wanted to make is that the array start continues in increasing order. Let me pull this back up. I'm grabbing PowerPoint next. Wrong one, that PowerPoint. Now, when we have this address space that looks like this, when I start declaring variables, local variables, arrays in stack frames, the very bottommost thing in a stack frame is that return address info, where the function goes when it's done executing. And if I have an array that's accepting information from a user and I don't do anything to check the length, it's going to put element 0, then element 1, then element 2, then element 3, then element 4, and then something eventually has the power to start writing over memory that's not been reserved for it. And eventually I can overwrite that return address. And again, this is the buffer overflow attack. I highly recommend you guys take computer security. That was a really great class. I loved it. One of the very first programming assignments is to write a buffer overflow attack that requires you to like really understand what's going on. So this class is like gold for getting ready for computer security. All right, back to what I'm talking about over here. There it is. So in fact, you can see the increasing array. So in this stack frame, I've got local variables. Here's my array. If I kept going, if I added another element to the array in my code, I stopped it at array max. If I were to go and just say, well, here, let's just initialize my array with some extra stuff. Here, I've got room for 5. Let's make this 25. If I go make that change, it's going to overwrite all of this information. It's going to overwrite A, it's going to overwrite B. I kind of want to see this. I claim that this is going to work. I want to see it happen. Let's go ahead and do this. And I'm not going to do 25 here. Let's just do 4 extra. So we'll make this 9 and see what happens when I print all this information out. So let me save that. Again, like I said, I wanted this. Yeah, here was me copying it back over to CSL. There we go. Compile and run it. So check this out. So A started out at 3. B was 4. Here's my array, 0, 1, 2, 3, 4, 10, 20, 30, 40. A and B were overwritten. So because I didn't stop writing out my array at the maximum element, I just kept going, writing beyond it, I actually overwrote the value for A and the value for B because of where they're located in memory. So this is one of those really common things, C programming errors. As the programmer, is your responsibility to know how big all of your arrays are and keep track of that yourself. The compiler does not help. There was no warning at all. Was there? I just compiled this. I've got warning, all warnings turned on. No warning that you overwrote the other data. By not checking, it makes this go faster in 2 ways. First, compiling goes faster. I don't need to worry about any of that checking. And running the code goes faster. It no longer needs to check at runtime to see if my array elements are in bounds or even valid. All right, I pulled this screen back up. I'm changing it back. I'm going to put it back exactly the way it was. That was just sort of me being spontaneous while recording, doing an experiment because I wanted to see what happened when I did that. I highly recommend you guys try this out on your own machine and see if you can overwrite that other data. The Linux version would not have done that because it moved the block of AB, PA, PB to lower addresses or higher on the list than the array. So it would have not overwritten those, but the array would have overwritten like whatever came after. All right, let's see. I need to get rid of this. I also want to print out one more thing here in this block. I want to know where ARR, where my array is actually stored. So here, let me grab, let's see, one of these lines. That one will be fine. ARR. I'm going to print out the value and the address of ARR. And just see what, I'm pretty sure this will give me some sort of error message when I try and do this. But I want to see what it says so I can talk about it. Save. Mike, you're not on Vim. Save that again. All right, let's try compiling this. Clear. So there's the compiling. Yep, warning format. The decimal format string specifier expects an int, but this has a pointer. That's because it's an array. We're going to see that arrays and pointers have really a lot in common. So right here, let me go ahead and change this. It expects, so array is actually a pointer as far as like the printf function is concerned. So let me go ahead, switch back over here, and change this to a P. Now it should be printing out a pointer. Save that real quick. Compile that again. Now my warning goes away, and I should be able to run this and get some extra information out about where my array variable is stored. I got this wrong last year. If you're watching the videos from the summer, that's a great resource. This is one of the places where I know I made a mistake and learned a lot since I recorded that lecture. I don't believe anybody pointed it out in the comments, and I'm not going to like go claim I made a huge blunder. It's pretty minor. What I had done before is I had said that array actually gets its own space in memory somewhere, when in fact what happens is it's actually got the same address as the very first element. So when you compile C code, let me see if I can break this down. All of the different variables, in this case I've got A, B, PA, PB, and ARR array. The compiler reads that and it puts the names that I chose in a symbol table. And then on the other side of that table, it matches that up with the memory addresses that it's going to be using. Okay, if I have a pointer that points to an array, that pointer gets a memory address where it's stored, and the value stored there is the first address in the array. Now, if I'm just creating a primitive array using the bracket notation like this ARR is not stored somewhere in memory. It's not a pointer to that memory address. It is that memory address. So let me try and make this a little more clear. Where's PowerPoint? The other PowerPoint. Hold on, that's the wrong screen. There we go. So I've got my array right here. On this line right here, I've got the first element of ARR. This is also where we have ARR without any brackets. And I'm not, this is probably, well, I need some more space to make that look good. This is not the best way to write this. There's not a good way to write this. Oops, typo, ARR. There we go. Technically, the symbol table inside of the compiler is just associating that variable ARR. It's treating it as a pointer that points to this address right here. And it's also giving, here, let me switch back over here. There were two pieces of data here. I printed out F4, and it's also located at address F4. So both of those. It's basically a pointer that points to PowerPoint. There we go. It's a pointer that points to right here, the first element, and it is that element. So it's a little confusing. This is one of the primary differences between arrays and pointers, so it is kind of important. As a programmer, it actually has very few consequences. It just means that if you declare an array using this notation, like this, it actually takes up 1 fewer memory spot than if I have a pointer to that array, which saves us 4 bytes. And this is also going to be considered constant. We won't be able to change this to another array. Pointers are really very powerful, and pointers are going to let us point to different parts of an array. I can switch from one array to another. So there are a lot of advantages to using pointers, but it does have to keep track of, like, not only does it store the pointer somewhere. Let me switch back. And I'll add a pointer picture to this in a second, but that'd have to store the pointer somewhere with an address, just like PA right here points to that value. I would need a pointer to this array that would point to address EF4. ARR doesn't take up memory. It's not in this picture at all. I've got it in parentheses here, and I guess that's the point. It's not in this picture, which I guess is like showing that something's not there is not super useful, but it's important to understand the differences between pointers and arrays, because they are so similar, and this is one of the minor differences between them. All right, next up, I just thought of another experiment that I want to try. I'm going to make my array a little bigger real quick. We'll make it 25 elements. So we're going to reserve more space. We're going to initialize more things, and then we're going to print out more stuff. Now, I didn't test this. It's getting late, and I just want to see what happens if we skip initializing and we just print out what's in this array. We should be finding that somewhere in there we've got a 3 and a 4 and some memory addresses, because that's it only, no wait, I take that back. That's if I reserve 25 places, that's not going to overwrite them. If I reserve 5 places, then we should see them in there somewhere. Let's try it this way first. So quick experiment. If this doesn't make sense what I'm doing, pause the video and stare at it. I'm creating a small array, then I'm printing out 25 values from it. In fact, let me just change this to 25. There we go, 5 and 25. And this array was in memory in front of all these variables before, AB, PA, and PB. And I didn't change any of them. I didn't initialize anything. So we're should be just looking at whatever the memory space is right there and an extra 20 elements beyond it. All right, so save this. Yeah, like I said, I didn't test this yet. Let's just see what it looks like. All right, cool. So here we go. I've got A, B, 3 and 4, got some memory addresses. And then the start of my array, elements 0, 1, 2, 3, 4, this is just going to be whatever garbage was in that memory because I didn't initialize it. So C does not do any initialization for us. And then let's see here. We got down to, yeah, here's the 3 and the 4. And above that should have been pointer to A and pointer to B. This is the decimal version of those, I believe. And in fact, let me see here. Yeah, here's 18 and 14. So 18 and 14. Yeah, looking good, looking good. And then the point is, these aren't 0. They were not default initialized. I'm actually looking at memory that overwrites another part of, or it doesn't overwrite, but I'm like out of bounds accessing things I should not have the power to access, but I do. It's not invalid. It's just really bad practice and leads to giant disastrous errors. All right, I just want to do that. I'll show you what happens if I don't initialize it. I'm going to go put that all back, and then I'm going to grab a pointer to my array and start talking about pointers and arrays and their connection. All right, I got that stuff put back. Here's what we're going to do next. I'm going to create a pointer to an array of integers. And to do that, it's just a pointer to an integer. Let's call this par from now on. Pointer to array right there. And when I initialize this, I need to initialize all of my pointers, otherwise they're just pointing to random garbage memory, because it's going to, there's something in the memory that it's reserving for that pointer. And I need to give it an address. And what we just saw is that arrays, when used like this, are actually addresses. This only worked because I needed to put in the address symbol for printf. So I do not need the ampersand sign in order to access the array. This is actually going to give me an error because the address, wait, no it's not, because this also worked. Hold on, this works. This works. Let me show you. This works. Yeah, compile. Initializing int from incremental pointer type. It's a warning. Unused variable. It does work though. Okay, so it's just noticing that these types don't match, but it does work. Wait, let me switch back over here. I've also got a huge array. I changed that to 25. I'm going to switch that back to 5. This should also be good because ARR is also a pointer. Save that. Let's go compile this. And now the only warning this is got a lot of stuff on the screen. The only warning I'm getting is that I haven't used my pointer to the array yet. Okay, so this is the preferred way to initialize a pointer to an array. And now let me go ahead and use this. One of the things I can do with this is I can go ahead and use the pointer to print out everything in the array. So where I've got ARR here printing that out, I can use PRR. Yep, let me just do it this way. I think I got all the right things changed. Compile that. I should now be using it. No warnings. We'll run that. And what I see here is first I'm printing out my array, printing out some information about the actual array. It's the first address. This is all the same stuff I just went over. Now, I'm also using the pointer to that array to print out the exact same information. And I'm using the exact same array index notation with brackets. We'll talk about a couple of different ways. The terminology for using brackets is called array index notation. So when I use brackets to access either an array or a pointer, and pointers can be accessed the exact same way with these brackets. And I'm getting the same value, 0, 10, 20, 30. The address of these guys, EEC. Oh, look, they moved. Awesome. Some of my picture is going to be bad now. But the point is, they've got the same addresses. All right, let me print out one more thing. I didn't print out where my pointer to my array is stored. So let me go ahead and copy and paste here. This one's printing out information about the array. I'll do the same thing for pointer to the array. The pointer to the array is not going to, yep. So pointer to the array is actually contains a memory address, so I do need the %p. And address of that is still an address. There we go. So now I'm printing out, yeah, all the right stuff. Let me go ahead and recompile. Run this again. And what I can see here is the pointer to the array, EF0, should be the very first address of the array, EF0. Also where the array is stored and where the address of array is stored, those should all be the same. Okay, and that array is actually stored somewhere completely, I'm sorry, the pointer is stored completely somewhere else different in memory. So these two are the same, EF0, EF0, that's because this is the array. The pointer to the array gets its own address, so EEC in this case. Let me see, that would be, all right, EEC is going to come right before EF0. Let me go put this in a picture. Just staring at these numbers and hexes is not working for me. I need a picture. One second, let me go make that. I've got everything in its new spot. So A is down here now at address F10. B is at F0C. So this should match up with what we see here. 10, 0C, yeah, 08, 04. Okay, so those look good. I've got the array in. Array starts at EF0, and goes through F00, F00. Looks good. And then my new pointer to the array is at address EEC. All right, there it is right there, EEC, easy to put in now that I've got a picture. And the value it contains is EF0, right there, EF0. So here, let me grab another arrow. We'll drop this up here. Because this is a pointer, it points to that array, just like that. And I'm covering up the text. Hopefully, you guys remember what that says. So here's the idea. It's a pointer to an array. It's located at this memory address. And when we dereference it, we're getting array 0. And this using bracket notation, just like we did our array index notation right here when we printed things out. You're right there, highlighted p array of index I. That basically is the same thing as dereferencing. And I'm going to do some math in the next PowerPoint slide to talk about this specific interaction between the array bracket notation and the pointer indexing and pointer arithmetic. So that's coming really soon. But I just wanted to put together this PowerPoint picture, this one, showing you that if I have a pointer to an array, It gets its own memory address. It points to the array in memory, and I can dereference it the exact same way I do with array bracket notation. The difference is that for array, I don't get a memory address for ARR. In fact, the compiler, if I ever request it, just gives me the first, well, basically the address of the first element back. No matter if I ask for the address of it or if I just ask for its value, both of them return the same memory address. All right, so that's the first major difference between pointers and arrays. All right, the next thing I want to do is show you that I can also print this out, printf, using the pointer notation, pointer dereferencing. So if I dereference PAR, that's going to be a decimal value. Should be a 0 because that's what's in array element 0. There we go. And yeah, that's all I want to print right here. So we'll just do star PARR. Compile that and run this real quick. Make sure I'm not making mistakes. So I can also dereference. So I can use pointer notation to go grab the value right here. I believe this also works with, yeah, let me just do one more thing. We'll also do it with dereference ARR, and that is equal to decimal value. I'm going to have to edit this if this doesn't work, but I'm pretty sure it does because they're almost identical. Compile. Yep, okay, so we can also dereference the array like that. All right, next up, the next major difference between pointers and arrays is that pointers are variables and arrays are essentially constant pointers, if we want to think of them like that. So here's one of the things I can do. I can go ahead and say R equals the old value plus one more. This is going to move it one integer size. Yeah, in fact, let's print this out again. So we'll do that. And yeah, let me just run this with just this much. Find out where the next mistake is right here. Nope, looks good. Okay, so dereferencing PARR, 0, dereferencing the array is still 0. Then I did, I want one more line, hold on. This line again. All right, there we go. So I've got it twice. Starts out 0, starts out 0. It starts out pointing to EF0. EF0 was the array element 0. Then we incremented it, and now it contains the value EF4, which is actually the second one. So the line I did was par equals par plus 1. Now the compiler already knows that it's a pointer to an integer, and so it knows that the size of integer is 4 bytes. So it's automatically taken care of that and incremented it by 4, not just 1. I'll go back with a PowerPoint and walk through this a little more carefully, but it went from F0 to F4. And it's because the compiler knows the size of integers on this computer is 4 bytes. And so when we dereference this one, I see that I now get the 10 because my pointer is now pointing to this memory location, not the original one. I upgraded it, I changed it. Also note that the pointer is still at the exact same place, EEC. Pointer is at EEC. So in the memory model, I pull this one up. What I did here was right here, this value, I incremented it. So instead of this being EF0, it's now EF4. And my pointer, let me grab my arrow, is now pointing one spot down to right there. That's all I did by changing the code. The pointer is still in the same memory location right here, but it's now got a different value. Whoops, here's the address, EEC, but the value is now different. It points somewhere else. We can't actually do this with arrays. Arrays are constant pointers. So here's what I did. I've got par equals par plus 1. If I do that with just the array, if I try and change where the array points, I can't do this. This is going to give me a horrible compiler error, and actually I think it might be one of the useful ones. Yep. Assignment to an expression with array type. So this is an assignment statement. I've got the equals there, single equals. Can't assign to an array. So that one's actually pretty useful. Okay, so this line right here is the one that totally failed. I cannot assign to an array. and that's what this is doing. These other two more options for incrementing an array, par plus plus should work, and par plus equals 1, or however many elements I want to shift by. Those are also going to reassign the value to the next element in the array and shift it down. We can see this used a lot in like loops, for example. Let me go ahead and I'm going to pause and just write one and show you using a pointer to index through an array. One sec. Okay, so we're looking right here. I've just added a quick loop. This is going to declare a pointer to the array, and it's going to start out pointing to the very first element of the array. While it's not equal to the last element of the array, and this is actually the array max is one element past the end of the array. So it'll still capture the last element. It'll get all the way 10, 20, 30, and 40. So the notation here, P is the actual address, and I'm comparing that to the address of the element one past the end of the array. Okay, so it's not equal to that. We're just going to keep doing stuff. And what we'll do is using each element one at a time. And all I'm doing is printing it out so we can see that it works. Jump back over to PowerShell where I've already run this code. It took me a couple tries to get that totally right. I had some extra typos in there. But anyway, it's printing out 0, 10, 20, 30, 40. It stops. It's not an infinite loop. Things are looking good. The downside to doing it like this is we lose the access to which index we're looking at. By using a pointer, we no longer, unless we have a special counter that counts how many places along we are. So this is useful if we want to go through and do the same operation to every single element. Like if you're like working through an array of characters, a string, and you want to make them all uppercase or something. We don't really care what the index is. We just need a pointer to that character so we can change it. But we do lose access to that to the index. So it's an interesting way to do things. It's got some power to it, but has that disadvantage also. I want to talk a little bit about how does array access really work. What's going on inside of the machine now? So in all of the other computer science classes that we teach, ARR just, we give it the bracket notation 3. This just gives us the third element of an array. So, but on the inside of the machine, what's really going on is that this ARR3 is actually being translated to the base address of the array. I've got that right here, element 0. That address is going to be offset by, I'm clicking the wrong spot, there we go, plus 3, because it's 3. But I also need to know the size of whatever these things are. 3 times size of int. All right, and that means that ARR3 is going to be equal to, let's see here, ARR is equal to OXEF0 plus 3 times 4. That's equal to 12 bytes plus EF0. That's going to be, what is it? OXEFC. Yeah, okay. So that's how we're going to, inside the machine, get to that particular element. Now I need one more thing because this is an address, and this doesn't actually, this much doesn't give me an address. It gives me the actual value. So I need to dereference the memory address. So that's going to be the dereference operator like that. So I need the star operating on this entire address after I compute it. Or the same thing, oops. Right there, I clicked the wrong spot. Operating on this much. And again, I throw a star in right there to dereference it, or star like that, something like that. So star to dereference to go get that value. Cool. So the next thing, we don't actually need to type that as programmers. Instead, the compiler is going to take care of knowing the size of whatever the data type is. So we don't need to type size of int in order to move from one element to another, accessing arrays. Instead, what we're going to be doing is, let's see here, ARR3 is going to be equal to just dereference address ARR plus 3. So this should work just fine to go give me the value at index 3 of my array. And the size of, wrong screen, size of is taken by the compiler because it already knows what type it is. Just makes it a little easier for us, and it makes our code a little more portable. If we go from a 4-byte integer machine to something that uses 2 bytes for the integer, we don't want to have to worry about changing the size of an integer anywhere in the code. So I mean, size of is great, but it's a lot of extra typing when the compiler already knows that's what we mean. All right, in general, let me just put this, we're also going to have ARR of I is just going to be equal to, gets translated to size of it like that, or we type lost a parenthesis right there. Okay, so this bottom version right here, let me move this up a little bit. There we go. This bottom version that we type, this is the array access bracket notation. Array, what did I call it before? Oh, I'm blanking on the name. It's getting late. Array index notation, something like that. Array index notation. That feels good. And this is going to be the pointer notation version. This is the one I want you guys to use in homework 2 when it comes out in a few days. To do everything, to just take care of doing all of the pointer math, the pointer arithmetic on our own, and not relying on the compiler to do it for us. As the compiler runs, we're going to see in the middle section of the course that all of the assembly language uses this notation right here and not the bracket notation over there. Okay, let me pull up my next example and I'll be right back. Alright, I decided my next example is to actually show you that this actually works. Even though I just claimed that using a pointer notation was difficult because we couldn't change the array, this is not changing the array. This is computing an address and dereferencing a new address. Nowhere am I assigning to the array. So that's what I'm going to do next. I'm going to go ahead and come back over here and just grab something that prints out a line. We'll make a copy of that. Here we'll print, let's go with ARR of 3, so that's what I just did. And we will print that out not using ARR of 3, but instead we'll use dereference, the address of the array, plus 3, just like that. Save that. Yeah, clear the screen, we'll compile, and we'll run this. There we go. Indexing the array using that pointer notation. You know what else is kind of fun? Don't ever do this, please. This it works. It's not technically against the rules, but what the compiler is doing is it's doing addition. It's grabbing an array element right here, and whoops, that way, and an address right there, and adding something to it. This is just addition. And if you are doing addition, you can also write. This is actually equal to I plus ARR, right? I can put the addition in any order I want. That's the commutative property of addition. And what that means is that I can also rewrite this one more way here. Instead of printing it out with this notation, I can also do 3 with the array in the brackets. So it's this with the 3 and the array switch, so the 3 is outside the brackets. This will work just fine also. As a programmer, though, nobody expects to see it like this. It's confusing, it's hard to read, no one recognizes it, but just, this is the one course where someone might demo this, so there it is, it works. There's no compiler error. This, believe it or not, is not against the rules of C. Alright, please don't ever write code that does that. You'll just confuse me. This is the only day of the year that I ever even remember that this works, and I'm lucky that I did. Alright, now I'm going to go set up my next example. I'll be right back. Alright, so the next thing I want to talk about is actually passing arrays to functions. Alright, so starting a new section right here. Let me just grab some new lines, put some of those in, break this up a little bit. And what I'm going to do is I'm going to be using a function that just prints out an array. So here's the code that prints out the array and the addresses of the array. Let me make sure I got the right one. can make that look a little better. So there we go, 2 blank lines. From 0 to the max of the array, we're going to print out the array and its address. Perfect, that looks great to me. All right, and then we're going to call a function that prints the array. So we're going to get the array printed twice. Let's call the function print array. And this is going to take an array. Let's give it that one. And need a semicolon. That should all be good. Well, I need to go write that function. So it's a void function. It doesn't return anything, and it requires an array. So let me go ahead and up at the very top, the compiler is going to need that to be defined before it ever gets to that line. What it really needs is the return type, so that down here it knows that if I have this assigned to a variable, that it should give me an error because it's a void function. It also needs to know that it should expect an array right here. So this is an integer array. Let's call it, I'm going to go with array to be like super original. I'm going to go ahead and put a size in right here, but we'll find in just a moment is that size is completely optional. I do not need that. And I'm also not going to be changing it inside the arrays. So make it const, just so that I can't change it. That looks pretty good, I feel like. All right, so that's my function prototype. You know what? I'm just going to go ahead and write the function right here. We can put the definition here. In the first lecture, I demonstrated writing the function prototype at the top of the file and then putting the function definition at the bottom. Just be consistent would be my advice is when you're writing code. Almost certainly you will have a boss somewhere that wants it done one way or the other. I'm going to do it right here so that when I change the function prototype, I don't have to change it in 2 places. And then I'm going to actually go back and move this so the function's below and the prototype is at the top and show you what happens when they don't match. Just to because it's interesting. The error messages are worth taking a look at. Okay, so I just want a function that's going to print out the array. I named it the exact same thing, so I could just copy and paste that line. Got a little extra there. Nope, we need one more closing bracket. There we go. All right, so print array is going to accept an array as a parameter, and then it's going to go through that array and just print it out. Still using array max. That looks good. Let me go to PowerShell. Compile that. Typos? No typos. Sweet. And run this. Okay, so we've got those 2 blank lines. Now I'm printing out the array and printing out the array again with my print function. Let me go ahead and just talk about this for a second. So check this out. If we look at the very first line, we see that it's at address FEE8. Okay, that's in the main stack part of the stack. When we go to array 0, element 0 in the function call, this is at EE8 also. EEC. All right. So what we've done here is essentially passed an array by value. Everything in C is passed by value, and what we're actually passing is a pointer. So the value that got passed is an address. So what we see is that when we print out the array, we're getting all of the same memory addresses. That's because an address was passed. So things like arrays look like they look like call by reference. It's deceptive, and that's why I wanted to do this example. I'm going to do the same example again with a struct at the end of the part 3 of this lecture. It'll probably be the 3rd video, and we'll see that actually gets copied, and each individual data pieces is made a copy of. So in here, I'm passing an array. It's the address that's getting passed, and so it's essentially a call by reference type of experience, even though the value, everything is called by value, but the value that got passed was an address. All right, let me go back to the code here, and just a couple of other little details. This size is optional. It doesn't care how many things. It just needs to know that it's an array. And inside this function, we as the programmer are responsible for knowing how big this is. So a lot of times you'll see functions to take the size of an array as another parameter. That's very common. I'm going to leave that out right here because I don't want to break everything. But I am going to go ahead and run this code again and demonstrate that. I'm also going to add a little note here indicating that I'm calling print array. And then we'll run this again. No typos, good. Demo, yep, there it is. There's print array now. And we can see that it worked just fine, even though I took out the size of the array. Oops, that's the wrong, not what I wanted. It doesn't need it. It just needs to know it's an array of integers. And the only reason it needs that int is for the size, so it knows when I'm incrementing, when it's doing this address computation, it needs to know that it's an array of integers so that I gets multiplied by the right size of. All right. One other thing that we can also do is, instead of using the bracket notation here, we can also call this as a pointer, because arrays and pointers are equivalent. So let me go ahead and run this code. I'm going to add one other little detail right here. Yeah, right here. I'm going to print out. Let's see, I already have this line. I printed out the array address right. Where was it? Yeah, this one right here. I want to do this again. Make sure I'm not actually telling lies. So this should print out the address of the array and the address of the array. I'm gonna copy this line one more place. So this is right after. Yeah, right there. So right before I call print array, I'm printing out the one in main, and I'm printing out the one in my function. So compile that, run it again. Oh, I didn't mean to do that every single time in the loop. Hold on. And you got this bracket in the wrong place. Bracket. There we go. That looks good. Blank line. Okay. I got this now. There we go. Okay. So check this out. I'm still getting all the same addresses. EE8, EE8. That's where all the data is located. It's called by reference, called by value. We've copied the address. Now check this out. Array is EE8 in main. That's the same here, EE8, and it's also EE8 here. That's the value stored in this pointer. So I'm declaring a pointer. That's a local variable, or a parameter. I'm sorry. Let me use the right language. A parameter. But this parameter is actually located at EC0. So this is going to be in the stack frame for the print array function. So this is a different address than right here. So let me go ahead and in PowerPoint. Yep, I've got. Let's see, where did I had a picture up at the very beginning where I had my main function. Let me go ahead and real quick. I don't need all this stuff. The one I care about is parameters. Call that. We'll shorten that out. Param and locals. I've got main. This was not main. This was print array. And by param and locals, the one I'm particularly interested in is ARR. And we've also got the return address information. So I'll shrink that down, stick it above here, above main, kind of run out of space. But so main has, there we go, a local variable and array ARR. When we pass that to the function, it created a pointer to that array and copied the value. The value that got copied was the address. So this is a pointer to the array in main. And that's why right here these addresses don't match. So this is the array in main, EE8. This is where the pointer is located, the EC0, somewhere in the stack frame. The stack frame for that function. There we go. And it contains the address of the array. This is what got copied. And that's why all these values are exactly the same. That's a tricky way to do call by reference. Okay. Okay, the next thing I want to do is introduce character arrays, also known as strings. There we go. Okay, so first we're just going to make a quick character array. Let's put in 10 letters. Let's see here. And I need to be a little careful because strings are terminated by a null terminating character. So here, I'm going to make my string right there in just a second. And what's going to go in this string is actually the character A, B, C, D, E, F, G, H, I, J. All right, that's too many, isn't it? I only save room for... There we go. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the very last character is going to be the null terminating character, which is kind of just a flag built into C saying this is the end of a string of characters. And there are just tons of built-in string functions that are techniques to work with strings that rely on the fact that all strings are going to end with a 0. Now, not the ASCII value 0, the actual number 0. Remember I told you you could use characters to do math with limited numbers of bits if you had a memory starved system. So at the end of this string there's going to be one more character, the null terminating character. This needs to be a comment. There we go. So that's what this is going to look like. Let's go ahead and we'll just print this out. So let's see here. We'll do it two ways. Printf. Let's see. I got a bunch of other stuff in the way. So we'll put some new lines in first. Then we'll do string equals %s is the code for printf to understand that what it's getting is an array of characters. Yep. New line. Close that up and give it my string. And then the other thing I'm going to go ahead and do this in a loop. Let's see, and in this case, let's go with, I want the index notation so I can go past the end of my string. And then I'll show you the version with the pointer. So let's see here, int I equals 0, I less than, let's go with 15. Let's grab some extras. So we'll go past the end of the string. That will show us that we do get a 0. I want to do I++. And then I want to print out a bunch of things. Here, let's go with printf. First thing we'll print is I, so that'll be %d, in my quote. And then we'll print out the character, %c. And then we'll print out the address. Let's see here, that's going to be %p. Maybe let's do str of %d. Instead of just that one. There we go. And that'll give us I, str of I, and the address. Yeah, that looks like a very good first attempt at this. Let's see what typos I made. God, that I got this right are small, I feel like. There it is. All right, what did I do wrong? I want to take a look at the very first error message. str is undeclared, first use. Oh, I put those in backwards. Yeah, it's getting late. Okay. No, my fingers are on the keys. So it's a character array. Character comes first. All right, now what mistakes did I make? Next up we have missing terminating character. Oh, I forgot the quote. There it is. Right there. There we go. No more errors. So I need // demo.exe. Perfect. Okay. I forgot the new line. This is no good. No good. Right there. File, run. There we go. Looking good. Okay, so here's my string, A, B, C, D, E, F, G, I. At string position 0, we have an A, and that's going to be at this address, 2061 FED6. All right, now characters in C are only 1 byte, so we would expect that the very next character to be at 7, and then 8, and then 9, 1 apart. We're no longer counting by 4s, A, B, C, D, E, F. Maybe I should have started with this. But here's the deal. A, B, C, D, E, F, G, H, I. And then this is a non-printing character, that \0 that terminates all strings. So it doesn't print. We just get nothing. And then there's some other symbols. This is just random garbage in memory beyond the end of my array. But let me go back and do one more real quick thing. Not only do I want to print out the value of the character as a character, but let's also print it out as a decimal value. And I can show you that it's actually really equal to 0. And to do this, this will just... So in memory, every character is represented by an ASCII code. Like A is 97, but lowercase a is 97, and lowercase b is 98. I could be wrong. We'll see what they really come out in a second because I'm printing them. And Printf is just taking whatever data it goes and reads from that memory. It's a bunch of bits, ones and zeros. And it's saying, okay, treat it as a character when you do this. And that's why it's printing out A, B, and C. It's translating into the ASCII. If it's a %D, it says, okay, treat it as a decimal. Print it out as a decimal. So we should get 97, 98. Let's actually see that. There we go. So 97, 98. I think that's what I said it was. And again, at position 10, or index 9, we have a non-printing character equal to the value 0. So what this means we can do is that we can write loops that will take advantage of the fact that a dereferenced pointer to this character will actually give us the value 0, which is going to be considered false in a loop. So one second, I'm going to pause the recording. I'm going to go get this line, make sure I get it tweaked so it actually is correct, and I'll be right back. All right, this is just a fun one. I just wanted to walk through this example using pointers to arrays in a loop to do string copy. So here I've got my original string with the A through I letters of the alphabet, and then the backwards Z, Y, X, I've got a second string, and I'm going to copy one string into the other. So I've got this one initialized from Z to R going backwards. I'm just going to print them both out, their starting values. I copied and pasted this line after string copy, that's the ending version. And in the middle here, I'm creating a pointer to the first string, str, a pointer to my second string, zyx, and then this is where the magic happens right here. There is so much going on in this one line. And this is the kind of power you would see from the programmers from the 70s who needed everything to be absolutely as fast and as simple. No, this is not simple. As fast and as short as possible, so that this line would compile as quickly as possible. Now what's going on here depends on like a dozen assumptions. The first one is that P and Q are both pointers to strings, that the string being copied, Q, is actually terminated by a 0 at decimal value 0, that null terminal \0 character. So what's going through? First thing that happens, these pluses and increments happen after the rest of the loop. So ignore those for a second. Star P is going to be dereferencing the pointer to that first string, which is going to be the character A, the very first thing. That's what's right there. Star Q dereferences the second string, that's a Z, and we're doing assignment. So it's going to take the Z and replace the A with a Z. Okay, that's what star P equals star Q does. All right, then we're going to increment. So both of these pointers, first one's pointing to A, which got changed to Z. It's going to increment and now point to B. Okay, the Q is going to increment and go from the Z, now points at the Y. All right, now because this is an assignment, the assignment has a return value of whatever was assigned. In that case, it was the character Z. So whatever the ASCII value for Z is, it's something like 123 or something like that, is not 0. So this is going to be a true statement when I use assignment inside of the condition for a while loop. And then the semicolon here just means that there's no function, no statement here, just a null statement like pass in Python that does nothing. And so the while loop continues. All of the magic happens inside of this while loop. Now, when we get to the very end of the string, remember there's a null terminal character, something like that at the very end of the string. Now right there, I actually drew it, it's right here, this one. This is going to evaluate to 0. So as soon as it copies that 0 as a decimal value into P to terminate the P string, str, so actually, it's this 0, the one at the end of the zyx, because I've got Q that way. Yeah. As soon as that happens, this is going to return that 0, which evaluates to false, and that terminates this string copy loop. So let me go ahead and run this. We'll print this out, and we see that it actually does copy. Let me compile this. Oh, it gives me a warning. Let me talk about this for a second too. This is just good programming practice. What I did was totally legal. There's nothing wrong with it. But because I'm using assignment inside of a conditional, the condition of a while loop, or a condition of like an if statement, they recommend using double parentheses just to give other programmers and myself later on a clue that I'm using assignment inside of a conditional. So just like that, that's the like signal to other programmers that we're doing something a little more complicated than it just looks like. I didn't just forget the double equal. I intended this. All right, let me go back, compile this again. Warning's gone now. We'll run this. We see the two original strings, A through I, and then backwards Z through R. And after the string copy statement, we now have both of the strings equal to the Z through R version of the alphabet. Alrighty. Yeah, just important safety tip. I think I'm not going to do any more examples. I feel like this is a really long video already. But strings must be terminated. There's got to be room for that terminal character. And if you overwrite it or leave it off or something, you'll see very strange behavior. Something like string copy without that terminating character could copy millions of characters when all you wanted to do was, the 10 from your array. If you don't save space for it, or if you accidentally overwrite the terminal character. Just important safety tips. I'm not going to do any examples of that. This is turning into a long video. I'd like to encourage you guys, though, to experiment with that. And if you end up with an infinite loop that you need to kill, remember that holding down Control and mashing C a bunch of times will kill a loop or a very long piece of code. If you do accidentally overwrite your \0 and it's copying forever, it doesn't stand for copy, it stands for kill. So it might be useful if you're experimenting. All right, that's going to wrap up this first part of the video, first video for week 3. Next up is two-dimensional arrays. I'll be right back with that in a few minutes.